In this video and the next, I'm going to explain how residue theory can be used to find certain integrals of the form integral from negative infinity to infinity of a function. Now, I'm going to show you the case when, first of all, the function f is a rational function. So in other words, it's a quotient of two polynomials with the further requirements that the degree of the denominator is at least 2 bigger than the degree of the numerator. So the degree of q is at least 2 more than the degree of p. And last of all, q has no real zeros. So there are no zeros of q on the real line. So an example of that would be an integral of this type. Notice that the integrand is a rational function, polynomial over polynomial. The degree of the denominator is at least 2 bigger than the degree of the numerator. And x to the fourth plus 1 is never equal to 0 for real numbers x. So let me give you kind of an overview now. If we have a function of this form, then first of all, we're going to extend the function f to be defined over the entire complex plane simply by replacing the x's with z's. So instead of looking at this function, we'll be using instead z squared over z to the fourth plus 1. Now, since the denominator has no real zeros, when I look for the poles of f, none of them is going to fall on the x-axis. So if this is the x-axis, and I find the poles of this function f, there might be some above the x-axis and some below, but there are not going to be any that lie on the x-axis. So to use residue theory, I'm going to set up a curve C, which is going to have one edge along the x-axis, going between numbers negative r and positive r, and then along a semicircle, and I'm going to choose r big enough so that all of the poles that are in the upper half plane lie inside that curve. So I'm going to choose r big enough so that all the poles of f in the upper half plane lie inside the curve. And we're actually going to ignore any poles in the lower half plane. Now to apply the residue theorem, I'm going to have to integrate counterclockwise around this. And let's call this curve C sub r. Then the residue theorem says that the integral around C sub r of f of z is equal to 2 pi I times the sum of the residues of f that lie inside, some of the residues at all the poles that lie inside this contour. So I'm going to indicate that here by saying z sub I is in, I'll write UHP for upper half plane. So I'll find the residues of the function at all the poles in the upper half plane and add them together and then multiply by 2 pi I. So that's what the residue theorem tells us. Now, on the other hand, I can also find the integral around CR by finding the integral along this line plus the integral along the semicircle. So let's name those two curves. So C sub r is the entire closed loop. Let me say that L sub r is this piece along the x-axis, and I'm going to use S sub r to represent the semicircle. So since C sub r is equal to L sub r followed by S sub r, I can write that this side is equal to the integral along L sub r of the function plus the integral along the semicircle of that function. And then by residue theorem, that's going to equal the sum of the residues of f at z sub I. What we do next is we're going to let r go to infinity. So we'll take the limit of all of this as r goes to infinity. Then under the circumstances that we've described here, this first integral is going to become the integral from negative infinity to infinity of f of x dx. So this first integral becomes the one that we're looking for. This second integral, under the circumstances that we've described here, is going to tend to 0 as r goes to infinity. And this side doesn't involve r at all, so that stays constant. So what that means is that the integral from negative infinity to infinity of f of x is going to equal 2 pi I times the sum of the residues of f of z, where you sum over all of the poles in the upper half plane. In the next video, I'm going to give you a little bit more details about why this integral becomes the one that we're looking for and why this integral tends to 0.